So let us crack on. So the last couple of weeks for class 1 we've been focusing on our exponentials and logarithms. For this class in particular we're now going to have a look at the applications of exponentials. So it's going to be all about how we can actually create our own exponential equations which model certain scenarios given to us in our Saxon exams. So we're going to start with what more or less looks like a fairly simplified version of the exponential. Right? We have just some n equals n naught b to the kt. Now yes, we're using fancier-ish coefficients, but it's really just a dilation factor, a base, and another dilation factor. The n is effectively the y value, the t is effectively the x value. There's no translation terms, there's no reflection terms. We don't have to care about any of that. Which is really nice because pretty much every application of exponentials can be done using this. We don't really need to think about any other terms. We just need to care about what am I going to use for my n naught, what am I going to use for my b, and what am I going to use for my k to sort all of this out. What we're going to explore next is how to decide what that's all going to be. So first up, the coefficient at the front, n naught, is typically referred to as the initial value of the exponential. The reason why it's often referred to as the initial value of the exponential is because the initial value of any function in a scenario is typically going to be found by figuring out what is the value when time t is equal to 0. Right? Initial. No time has elapsed, it's the start of the experiment, it's the start of the scenario. And if you were to sub in t equals 0 into such an equation, well, you'll see pretty quickly the only thing that's left over, the final value, is the same thing as whatever that coefficient at the front is. Right? The exponent goes to 0, anything to the power of 0 goes to 1, anything times 1 is just itself. So, if you are given any information that has to do with the starting value or the initial value of your scenario, you're going to go right ahead and replace whatever this coefficient is with that value. Any questions there so far? There is technically a bit of a caveat, which is in the unlikely condition that you have a plus c, some vertical translation or some other term that is tacked on as a plus or minus at the end, the initial value will now be split between those two things, because if you do the exact same thing of subbing in your t equals 0, well, you're going to have that floating c just sitting there as well. So your initial value, you'll have to figure out how to split between that. I've never seen that come up, so it shouldn't matter, but I figured it's worth pointing out that, hey, if you do have something else in there, whether it be a constant or otherwise, that will make the idea of just setting the initial value a little bit harder, because you have to now split it between the two. But okay. Next up, the base of the exponential. We're setting the base here. How do we choose what to set that? Well, if we think about what the base of the exponential actually does, it is the number by which we are repeatedly multiplying. All right, it's effectively like a growth factor that's going to choose or determine how fast it'll rise or fall. So if we compare what look like fairly similar exponentials, we'll see that they have drastically different outcomes as far as what comes out of the y values. 2 to the power of numbers rise much slower than 3 to the power of numbers, even though the base is only 1 digit removed. Now, how do we plug that into our application questions? Because we understand that it's a growth rate factor, we're going to choose our base to match it with the growth rate, or decay rate, if that's a thing. But it's still, you know, how fast or slow is it growing or decaying. A very typical example is going to be some population growth or cell growth. Let's say it doubles every fixed period. The fact that it's doubling means you're going to choose your base to be 2. Right? If we see the f of x values here, every fixed period, every integer value of time, you double whatever was previous. 2 doubles to 4, 4 doubles to 8. If it triples, you're in that g of x range now. 3 triples to 9, 9 triples to 27. Any questions at all on what we're considering when choosing the base for our exponential? Cool. Last up, the coefficient k that goes on the exponent. There's a couple of things that happen here. The most likely outcome, honestly, is you're CAS solving this thing. You're actually subbing in a known value that exists in the scenario's background information, and you're solving for k. But that's something we've been able to do forever, right? If we know enough of the coefficients and we sub in a point, we can solve whatever the unknown is. So I don't really need to explain too much about that. It is just a CAS solve, or just a quick algebra rearranging. What I'm going to show is, under some circumstances, you can actually just determine what the value is without even needing to solve for it. One of the ways is if the fixed period of time is given to you. Right, if we're doubling every 15 minutes, for instance. Because we are doubling every 15 minutes, what we're going to essentially do is apply a coefficient on our t value such that rather than it wrapping over to the next integer every integer, you wrap over to the next integer every 15 integers. So what do I mean by that? By having this divided by 15, it will not resolve as 1 until t equals 15, right? You got t equals 1 gets you 1 over 15, t equals 2 gets you 2 over 15. It's only when you get to t equals 15 that you finally go from your initial value of 1 to a double value of 2. Then again, the next 15 ticks is what finally causes it to double for the next one, so on and so forth. This is what we're trying to achieve here by doing it. The reason why this doesn't usually end up playing out is because most of your fixed periods are an integer value, doubling every 1 year, 15% growth rate every 1 month. In both cases, your k is nominally going to be 1, unless they do other things in the question to circumvent that. What's changing there is more so what the time frame is, whether it's in terms of months, years, or whatever. So this is a rare thing that you'll be able to sub in and plug in directly what your k value is. Usually it's going to be some sort of CAS solve or algebra rearrange to get your k. That's about it until we get into some miscellaneous stuff. Any questions there so far? Sweet. Okay, now how do we break the rules, or how do we increase our nuanced understanding of the rules? Sometimes you won't be given a growth rate. It won't say doubles or triples, it'll just say it grows, right? It won't even say at which rate. The strange thing about that is, if they don't specify a base, you can actually just choose whatever base you want, because the other coefficients that you solve for, namely the k value, is going to compensate for what you chose as your base. Because if you think about what's happening, both k and the base both contribute to growth. K, in this case being a fraction, is slowing things down, but it could just as easily be a whole number. It could be like 3t. So now t takes a third of the time to loop over to the next integer rather than longer. Similar with the base, you could choose the base to be bigger, but you would compensate that with a smaller coefficient. In fact, if you've done CAS related stuff with the exponential and you've control entered, you might sometimes find that what you plugged in as your definition of the exponential is now no longer the case, and they've condensed it all the way down into just a base with no coefficient in the power. Sometimes the CAS will do that because there is such a way to combine them all down. All that said, basically, if you aren't told anything about growth rate, if there's nothing that you could reasonably determine your base to be, just choose whatever base you want. Base 2, base 10, base E, doesn't really matter. All that will change is the k value, and the question will be worded in such a way where if they care about a specific k or they care about a specific base, they'll put the information in there to force you to use it. This one's more of a definition thing. Generation time. What they mean by generation time is the time in which it takes a batch of cells to double. So when you're told the generation time of a thing, not only are you told the time in which it takes to double, but because you're told it doubles, or it's implied that it's doubling, you're also told the growth rate. So this will be a base of 2 and a time of whatever number they gave you. Next up, you'll start seeing some applications of decaying exponentials. These are the ones that have the negative in the coefficient, which is one of the first ways you can create a decaying exponential. Your k value might just come out to be negative. Alternatively, you can also cause it to decay by choosing the base to be between 0 and 1. So when you would use what sort of depends on what information you're given. K being a negative number kind of just happens when you solve it. You don't really force that. This is normally when you have like this scenario here, where you're choosing your own base. The k would just come out to be negative to force it to decay rather than grow. This one you're more so doing when you do know growth rate. If it's like a population is declining by 5%, you're going to choose your base to be 0.95. Right? You're going 5% backwards. And that's how you then create your decaying exponential. The coefficient k that goes up the top will then be positive. Last definition thing, the half-life is the time in which it takes a radioactive material to decay to half of its initial value. So again, that's also sort of like a double piece of information, just like generation time telling you both time and growth rate. This one tells you value and time it took, or at least implies the value, as long as you knew what the initial one was to begin with. I know these are tough questions, and so for that reason I've actually created a full suite of work solutions for the entire Unit 1 and 2 book that covers this stuff, and so that should be helpful in our exploration into this sort of thing. But we're going to try and have a crack at them ourselves before relying on such things. Do we have any questions or clarifications before we go ahead and do that? If not, have a crack on with 1A. See if we can get this sorted. A population of 1,000 E. coli bacteria doubles every 15 minutes. To make life a little bit easier, I'll drop the entire applications PDF in the chat as well. Once that downloads, you'll be able to read up on, or refresh your memory on, how we assign each of those terms. So yeah, take your time, have a read, see what you can, see what you can figure out. For question A, we're just trying to figure out what the formula for the exponential equation would be. So all of them start out as some n equals n naught b to the kt. We got to figure out n naught, b, and k. N naught is always going to be the initial value that's given in the scenario. So by initial value we mean, in this case, population, right? because it's a population equation. Determine the formula for the number of bacteria, the population of bacteria, for time t minutes. So we're going to have an n of t equation. N naught is just going to be whatever the number of bacteria is at the start. And so, for that reason, population of 1,000, N naught is going to be 1,000. Next up, the base. So, base was all about growth rate. If we have any information about growth rate, we can set our base immediately off of that. If not, no worries, we can determine our own base, and whatever we choose for k, or solve for k, will come out to compensate for it. So you get a bit of flexibility with these questions, oddly enough. So this one says we have a population of 1,000 E. coli. It doubles every 15 minutes. There is a keyword in there, doubles, that's going to refer to the growth rate. Because it's doubling, we're going to choose our base of 2, right? Doubling. If it was tripling, we would choose a base of 3, quadrupling 4, so on and so forth. Base B is going to be 2. Specifically, it's doubling every 15 minutes. So that's actually going to help us with our k value, the coefficient that goes on the t. Now, as I sort of said before, you can choose a different base and get a different k out of this. So when it says determine the formula, it's a little bit incorrect because technically speaking there are multiple ways of writing this exponential to determine the same thing. But based on what we understand before, if we have information about what that fixed period of growth is going to be, which we do, 15 minutes, if we take a look back at the notes on this, and you'll notice it's the exact same example. If it's doubling or growing every 15 minutes, well, so long as your time t is in terms of minutes, you can now set your coefficient to be 1 divided by whatever that interval is. Because that means that every t value from here on has to reach 15, or some multiple of 15, to roll over to the next double. So, in this case, k equals 1 on 15. Giving us a final exponential, n equals 1,000 times 2 to the power of t on 15. This being Cas, we want to validate it. Do we in fact get the behavior that we were expecting? We can achieve that. Function is equal to 1,000 times 2 to the power of x over 15. So if we do at time t equals 0, we should expect whatever the initial value was, population of 1,000. If we then do 15 minutes later, we should double, and sure enough we do. Any questions about that one? If not, move on to part B. How long is it going to take for the population to reach 10,000? This is a very standard question across literally all the areas of study. It doesn't even matter. This is an exponential. We solve this the same way we do for any function that we know of. How long will it take the function to reach a value of 10,000? There's only one way to do that, which is what? In the cas, we are simply equating that to whatever the value is. So population to reach 10,000, set the population as 10,000. This is a population equation with respect to time. So if we're told population information, that is our y value. And if we're trying to solve for time, well, we're going to just do comma x on that, get the actual value. It did say it's the nearest minute, which would give us, what's that, 50 minutes? Yeah, because time t is in terms of minutes. Cool. Okay, next up, half-life of plutonium, 2400 or 24,000 years. 10 grams are present now. How long will it take until only 10% of the original sample remains? So this is the kind of question where things are going to get a little bit more challenging, because there's, well, it's just different information, really. It's not necessarily more challenging or so, but it is one of those things where we're going to be calculating our value for k, and we're also told nothing about the growth rate, or decay rate, rather. Kind of are. We're told the half-life, so that implies a decay rate there, absolutely, but it's not immediately obvious what that's going to translate to for the base. So for that reason, we're just going to make use of the fact that we can choose whatever base we want. I'm just going to stick with the base of 2, because what you'll see is that when you choose a base of 2, your k value ends up being something a little bit interesting. From there, 10 grams are present now. So if 10 grams are present now, that means at time t equals 0, there are 10 grams. So in other words, we have our n equals n0, where n is going to be the 10. The base we're choosing is the 2. And all we got left is the kt. We need to now solve for k in order to complete our equation before we can answer any questions. Which is a good point to emphasize, right? We need to make sure we have an equation before we can answer pretty much any question. So you'll notice I haven't even read what they're asking us to do yet. I'm just focused on creating the equation first. So to solve for k, we're told the half-life is 24,000 years. So that means that in 24,000 years from t equals 0, we will have half whatever we started with. So if we started with 10, we're going to now have 5. That is a point. That is the point 24,000, 5, right? X value or time value of 24,000, and Y value or mass value, grams, is 5. Plug in 5 here, plug in the 24,000 there. Only thing left is K. So let's do that. H of x is equal to 10 times bracket 2 power of k times t, I guess just x, and then the point. So we're told h of 24,000 is equal to 5. We've replaced the x and the y, only thing left in that is the k. And what you notice by choosing a base of 2 is that the k value ended up being the negative reciprocal of what that time value was. So choosing a base of 2 is usually fairly strategic for these kinds of questions, because it means you don't actually have to do your CAS solve there. You will just get that kind of k value. Now you've got to be very very confident to do that in the actual SAC and not just do the CAS solve, because it doesn't take you that long to do. But rest assured, this is a thing that's you're going to find is quite repeatable. So if you do want to chance it, go ahead. But my personal recommendation is do that in your homework, not the actual SAC. It'll take you 2 seconds to CAS solve it. But yeah, we have our k value, which means we have our full exponential. I'm just going to go ahead and actually we can literally just define k. It's a nice little hack there. We already defined h of x. I don't have to redefine it. I just got to define k, and it'll chuck it in there. But okay, we now have our full exponential. Now let's have a look at what's actually asking. how long will it take until only 10% of the sample remains? So if we started at 10, 10% of that is of course 1. So in other words, this is now asking how long it's going to take until we have 1 gram left. Well, this is a mass function, grams is on the y-axis, so that means we're going to set the function equal to 1 and solve for time, which in the CAS is x. H of, well, not that, h of x is equal to 1, comma, x. And as we expect, it's quite a large number, almost 800,000 years, which makes a decent amount of sense because the half-life was 24,000 years. It took 24,000 years to go from 10 to 5. What's not so obvious, maybe, is that to go from 5 to 2.5 is another 24,000 years, which is why having such a large number like this might make a bit more sense, because every halving takes 24,000 years. This is the nature of exponentials. We're just seeing them in the backwards direction, right? It's that there was a Neil deGrasse Tyson thing where he gave the example of like algae growth in a pond. You leave it overnight for you leave it for a year. You come back and half the pond is filled with algae. You know it doubles every day. How long do you have until it fills the pond? You have a day. Even though it took a year to get to half of it, it takes only a day to get to the last little bit. This is that, but in reverse. Anyway, so what do we do there? Well, we took as much of the information in the question as we could to start, right? We had that initial value of 10 grams, so that got us our starting point. We had no reasonable information regarding the base, so we just chose a base. Typically, base of 2 is quite nice, because that gets you a nice-ish value of k, which we got by solving. You're solving at a point. If you choose in fact, I wonder, did my solutions have a different base in there, or did I also choose 2 there? I did choose 2. Pretty sure the solutions in the book, in the actual textbook itself, choose a base of 10 by default. Let me see if I can spot that, just so you can see that either way. I guess we can just solve it on, yeah, let's just solve it together actually. So, what if we chose a different base? That means coming here and choosing, I don't know, base 10. Let's keep that the same there. Let's kill our variable of k and go through the whole procedure again. So the first thing we did was that. This is now going to get us a different k value. You can see is quite a bit nastier. We redefine that, and then finally we do the exact same thing we did in the Control Enter in the previous question, and sure enough, if we compare the 2 outcomes, these are the same thing. Furthermore, if I Control Enter on the function I just created, that doesn't look like anything I just made. It's because of the same thing. There's a mathematical way of condensing the k value into the base. Don't ask me what it is. I'm pretty sure it's transformations related, using the logarithm identity, the one where you have the log in the exponent. It's something to do with that, I think. You obviously don't need to know how to do this though. Just thought it was worth pointing out. This is what the CAS is doing behind the scenes, which is why you have 2 separate expressions of the same function. Cool. Next up, question 3 is basically the same thing. Does anyone want me to redo? Actually, is it? Hang on. It's similar. Yeah, it is actually different enough, worth pointing out. So once again, half-life, different value, of course. The cloth fragment now has 40% of what it contained originally. How old is it? Now that wording is a little bit suspicious because usually when we say something now has a certain value. That's the initial value. However, we're also told that there was an original amount as well. So we've got to use a bit of critical thinking to figure out what was chronologically first, in which case it is going to be, we're going to take our initial value as whatever amount of carbon-14 there was in the original cloth. Problem is, we're not really told a number here. We're told percentage. We're told it has 40% of whatever it started with. So, if we think about the things we're trying to solve for, we need to figure out what our N0 is, what our base is, and what our K is. We don't have information for any of that, actually, because our N0 is percentage based off of N, and the base, well, there's no, again, it's the half-life thing. We don't really have a specific growth rate. So the good news is we can just choose our base to be whatever we want, right? So let's just stick with the base of 2 for now. N equals N0 2 to the power of KT. But what are we going to do about the fact that we don't have access to a numerical N0? Well, we can still work on it based off of the fact that we have the percentages, because it's 40% of what it contained originally. So if it contained N0 originally, what we have is 40%, 0.4 of N0 is equal to N0 to the KT. Right, this is our final value, which is 40% of whatever we started with. We're doing it proportionally rather than with the actual numbers themselves. What's good about that? N0 is a common factor across both. N0 is a common factor across both. Being cancelled out means that only K is, well, sorry, there's going to be a T in there as well, actually. We're a bit jumping the gun on this, perhaps. So this is one of the things you can do with that. Now, we jumped the gun a little bit. We're actually initially supposed to be applying this to the half-life equation. Half-life of 5,730 years. Half-life is the exact same idea, but with the coefficient of 0.5, because it's half of the value. So 0.5 N0 is N0 2 to the KT, but because we're told the half-life is a number, is a time value, we now have a replacement for our T. 5730. And now we're happy. Now we only have K in that equation, which we can now solve. I'm pretty sure it's just going to be negative 1 over 5730. Let's validate. Where am I going to start this? Let's grab that one. 2. I'm just going to set that as 1. Yeah, it's going to cancel that anyway. Just some coefficient. We'll kill the K. And then we have so 0.5 is going to be equal to h of 5730, comma K. And there it is. So again, one of the benefits of choosing our K value, our base value appropriately. Yep, we have our K. Once again, define it so it fits into the function. We now have that with some whatever N0. We're just going to leave the N0 as 1 to just say it's the whole amount, whatever it was. So when we then go ahead and try to figure out how old the fragment of cloth is, given that it's 40% left over, we'll set 0.4 as that right hand side, and now just solve for x, which we can safely do knowing that we've already solved for k. It's the only thing left in the equation. So that gives us a time of 7,575 years, Does that make enough sense? Well, it should be bigger than the half-life at the very least. Half-life will get it down to 50%, and that was 5,730 years, which is in fact a smaller number of years than what we just achieved here. But comparable enough to where we're probably happy enough that we've done our math correctly here. So the lesson for that one was, even though we didn't have values specifically for the initial value, because it was written proportionally, we're able to write our equation in such a way where we can cancel it out and never actually need to know what n naught was. We can leave it as the coefficient 1 or whatever, really. Any questions there? Okay. This one is quite a detour in the sense that it's just giving you the equation flat out, and all the goal from here is just to analyze it. I feel like pretty much all of the effort in, or the difficulty in these kinds of questions is the creating of the thing itself rather than the analysis of it, because the analysis of it you do the same way all the time, like for any other function, right? Find pressure at height 5 kilometers. Well, it's a pressure in terms of height equation. So height is going to be 5 kilometers. You set the h height to 5 and see what comes out. Find the height when pressure is 400. Set pressure to 400. Has solved for h height. Like, these are things we've done before. In fact, if we just sort of take a little peek at what that looks like, they're one-liners, especially when you have your CAS. Cool. Alright, let's see if there's anything super unique to start having a look at. Okay, 500,000 at 12 PM on a Sunday, 10% every hour. That's kind of like this one. Liquid, T drops to that. Yep, so temperature and time as opposed to, you know, half-lives. Yeah, why not? Let's talk about this. So we got two equations we're working with now. Both of them are given to us, so again we don't have to worry too much about creating the equations, more so analysing them in conjunction with each other. They have a common t, and the y value is going to be populations of American states. The analysis of these should be fairly simple. First is just getting you to plot them so you can see visually what's going on compared to the two. You can kind of get an idea of which one's going to be growing faster than the other, because although this one has a initial value that's bigger than that one, this coefficient being double the coefficient of this is going to mean the growth rate of this one's going to be significantly faster. Granted, it will still take time to catch up, but I guess we'll see as we plot them, because the first thing it's asking for is, hey, when are they equal? And I have a sneaking suspicion that when they're equal, the time it takes to make it equal is going to be, to go from 0 to equal is going to probably be more time than going from equal to twice, just because of the growth rate difference being so large. But that's just hypothetical by looking at the way the equation's written. Obviously we'll prove that by plotting it out and solving for it. First up, 1.2 times 2 to the power of 0.08x, and 1.7 times 2 to the power of 0.04x. So you can see already it's actually getting crossed over. What's a reasonable domain here? T is number of years since 1950, sure. Let's just set this to 100. and give us a big y value. Okay, maybe too big. That'll do. So again, we can see the pink one with the slightly bigger coefficient is, yeah, rapidly increasing, or much more so than the other one. First question, when are they equal to each other? Well, we've done a lot of this before, right? CAS solve, equation 1 equals equation 2. Population equals population. Just in case anyone's forgotten, when you define those things in the graphing tool, you can grab a copy of them with this variable button that's kind of blurred. There we go, yeah. VAR, you can see everything that's defined in the CAS, of which the things in the graphing tool are considered defined. That's going to be 12.56, which if we have a look at where that roughly is, we can validate that we've done the right thing by quickly checking for intersection. 12.56, sure enough, right there. Cool. That's when they're equal to each other. We also want to know when they're double, where when population P, the one that's growing faster, is double the population of the one that's going slower. What do we do there? Anyone want to take a stab at how we're going to be modifying this? It'll still be a CAS solve, absolutely, because it's a very similar question. Might be easier if I leave the graphs open actually, so you know which one's which. F4 is the pink faster one, F5 is the green slower one. If I want to know when F4 is double F5, what am I actually going to CAS solve for? It's a bit of a trick. People get this backwards quite a bit because they think, oh, one's double the other, that means I should put the double on the thing that's doubled. It's not quite, because it's double whatever the other one was. So if F4 is twice as big as F5, you actually want to put the coefficient of 2 on the F5 because it's twice as big as F5. If you put the coefficient of 2 the other way around, you'll get the opposite effect. And quick sanity check, yeah, it is indeed a bigger number. Now, oddly enough, didn't quite pan out what I thought was going to happen. I would have expected that the growth rate difference would mean that 0 to 12 would be bigger than 12 to 37 here, but it actually didn't end up being the case. But anyway, that's the idea. That's just a bit of analysis of the graphs in conjunction with each other. Nothing too crazy. Okay, there's a bunch of other questions to have a look at here. Let's see if I can spot anything that's worth talking about. Here's some where they give you the base and then you're solving for a specific k. That's when they're able to actually say calculate k. You'll notice in pretty much every other question we did, they didn't say calculate k because they didn't give you enough information to force a particular k value. This one here, the interesting part of this is the limiting value. What does limiting value actually mean? Well, the notation they're putting in there is reminiscent of a certain thing. Anyone want to take a crack at what they mean by the limiting value, especially given this notation?
Domain?
Domain? Yeah, so this is referencing domain, right, in the sense that t is approaching infinity here, little t. And since t is in terms of minutes, that's going to be the x-axis, yeah. They are specifying the limiting value of capital T though. So capital T being a y value. We're not necessarily thinking domain for that. it's going to be a specific value. What are we thinking it's talking
Maximum.
maximum? Would it be maximum? Could be, depending on the shape of the exponential. Um, it's could be a max or a min usually.
Yeah.
It's going to be based off of. Actually, is it? Let's have a look. It's double decaying, so this will be a maximum actually. Yeah. Did you look at that ahead of time to see if it would be a max or a min?
So,
Did you look ahead of time to figure out if this would be a max or a min?
no, I just kind of just assumed because I've seen that
Hmm.
this kind of graph before, and
Oh yeah,
also based off the thing, kind of the lowercase t to infinity felt like a bit of a
yeah.
hint.
Okay. Yeah. So if you understood the graph, the way that shape is, because it's a base between 0 and 1, it's going to flip horizontally. It's going to cause it to flip vertically. So yeah, it will plateau at a max rather than a min. Um, what they mean by the limiting value specifically is limits, right? If you remember limits as t approaches infinity, it's just what happens when I chuck infinity here. Really, it's just saying, where's my asymptote? So if I chuck t equals infinity here, this becomes effectively 0 because you got this base between 0 and 1. You're repeatedly multiplying decimals between 0 and 1. So this will go to 0, leaving 25. That's how you can analyze it via the actual equation itself. You can also just plug this in your CAS and either insert t equals infinity into the exponent or do the limit. Both works. Let's have a look. Function equals negative 40 times bracket 0.98 power x plus 25. For actually inserting the infinity, it's on the pi symbol. So the same way you put pi, you get the infinity symbol. If you do that, it'll spit out 25 limiting value. Alternatively, if limits was what you thought of, then limits is also correct. Both of those will get you the same number that you're looking for. Just to put in perspective what the graphs were looking like, because we did talk about the graphical way representing like why is this a maximum. Well, it's because you're getting a double reflection and a shift up by 25. That plus 25 is the asymptote. So if we shove this up to like 30 and yeah, why not 100? You can see that it's curving and eventually will plateau like that. So yeah, nice find. It's good to be able to quickly look at the graph and roughly understand what the shape is going to be because it saves you a bit of time with this sort of thing, or at least it gives you something to confirm your suspicions. It's good to have an idea of what you think the answer is going to be before finding it because that gives you another point of validation. Anyway, determine little t for which capital T is 0. We don't even need to talk about exponentials for this. This is just something you do for any function. If capital T is 0, set it equal to 0. CAS solve for little t. Sketch the graph, we just did that. Comment on the model. That's very vague. So what I'll do is I'll bring it back to the scenario. So what is it about this that is happening in the real world? So like, yep, we're told the tub of ice cream is kept at negative 15 degrees Celsius. What's happening? Like, this is your graph of the temperature of your ice cream. If we were to describe what's happening to our ice cream in the real world, based on the picture of the graph, what's happening? This is a temperature time graph. You can be as vague or specific as you like. It's a very vague question, I understand. You've come off mute, but I haven't heard anything yet. Hoping it's not an audio bug. It might be. Uh-oh. But yeah, anyway, so audio bug aside. This
Sorry,
would
can you
be...
hear me?
Oh, yeah, now I can. There we go.
Okay, what was the question again? Sorry.
So the final question was like comment on the model, which was very vague, of course. So I'm putting a few guidelines around it, which is, based on the picture of the graph and the scenario itself, we're told tub of ice cream taken out the freezer. It's kept at negative 15 degrees Celsius, but our temperature graph is telling a story. What story is it telling? If you really, yeah, just summarize what's going on with it.
Yeah. Yeah, I don't know if I've done something wrong, but my graph kind of like it continues like arcing upwards, but like at a decreasing rate.
Well, it should, yeah, it should
Is that
arc
yeah,
upwards
is
and then slowly
yeah,
plateau off.
yeah, that's kind of what I've got.
Yeah, so it
And then
looks. You probably just need to change your settings. I've got like up to 1,000 here, and a high
okay.
value of
Yeah,
30.
yeah. Yeah, I think my scale is just a bit small, that's why.
Yeah, like if we saw even when I set it to 100, that kind of looked like a logarithm almost, if I remember correctly. Is that right? Yeah, it almost looked like it had logarithm
Yeah,
behavior.
that's why I was a bit yeah, that's why I was a bit confused at the start because I didn't expect the graph to be that big, so I had to just keep
Yeah, well,
zooming
we
in.
knew at least what the y value should be. If the asymptote's at 25, then we know I'm going to set it above that at the very least. And we know it's got asymptote, so if it doesn't look like it's asymptoting, just, yeah, keep adding zeros until it
It,
gets there.
if a question did ask us like comment on this model, is it just describing the graph or
Yeah, do your best to use the terms in the actual question, like the scenario itself. So, like, rather than say the temperature increases over time until it reaches a final value of 25, you might say something like the ice cream is now out of the freezer, and so it is warming up until it reaches room temperature of 25 degrees.
yeah, so commenting on the movement of the graph based on the scenario they gave us.
Yeah, yeah. Now, it's not going to say that. Comment on the model is something that just doesn't get written in these in SACs and exams, especially not the exam because it's so vague. But they'll usually put guidelines around it and be like, um, yeah, yeah, like when they say like, what does this value represent? That might be a bit closer to what you might see. What does that value represent in terms of the scenario? Well, 25 might be room temperature because we're told it was taken out of the freezer. And as we know, all things sort of tend towards the temperature of the room, whether they're hotter or colder.
Yeah,
Sweet. Again, we're saying limiting value, limiting speed, limiting anything. It's the same idea. Limiting is just your limits, or subbing in t equals infinity, or just knowing how this works, right? Like if you go to infinity here, that's a infinitely negative exponential, so that's going to be 0, which means 1 minus 1, so it's going to be 0, right? Anything with a massive fraction there is effectively 0. 3 to the power of 0 is 1, 1 minus 1 is 0, so we're tending towards velocity 0. Um, of course, you would just sub in your values and prove that, just to be super safe in the SAC, but good to be able to do that sort of thing. Otherwise, yeah, same idea. Limiting value. Now things are talked about in terms of percentages, but because our initial thing is a percentage, you don't really have to consider this any differently. Like our equation y values are percentages already. It's not like you're starting with numerical data and have to figure out percentages of that numerical data. It is just saying, okay, cool. If I have a p-value of 0.68, it means 68%. So when they say 75%, they mean literally sub in 0.75 as the y value and cas solve for t. These are more similar to what we do with our other function that we're trying to find the rule, where you've got a number of coefficients and a number of numerical information to solve them via simultaneous. We see this a lot with the polynomials, yeah, all the miscellaneous functions and stuff like that. You'll just cas simultaneous solve with these. Some of these you might be able to do by hand. Technically everything doable by hand, but you'd rather not. Although this one, apparently they're forcing the one place where they've emphasized don't use a CAS for. So good luck with that one. Let's see. Here's another bacteria thing, but they're also giving you... so here's a bit of an interesting part. So sometimes they'll give you the generic rule they want you to use, but not really fill it out. The difference here is that they've actually given you no option for a K. They're forcing you to have a coefficient K of 1. So the idea of us being able to set our base as whatever we want is no longer valid here, because the condition under which we were able to set our base whatever we want was based on the fact that the K value that you would get would compensate for it. So if we can't compensate with K, we have to do something with something proper with the base. Let's see how that's going to work. Number of bacteria increases exponentially. When observation started, 1,000 bacteria. 5 hours later, 10,000 bacteria. So realistically, it is just a repeat of question 13a here. It's just a worded version of these points. You can think of this as time t equals 1 and bacteria equals 15. Time t equals 4, bacteria 1875. So again, just a repeat of that. Once you have the rule, the rest of these should be fine, I think. What is it? CAS solve for 5,000. CAS solve for 1,000, a million. Sub in 12. Yeah, okay. Same thing. These we skip. Very certain that a lot of schools don't put stuff like this in the SAC. This is where what you do is you put this data into a table. If you look at your CAS, you got this list and spreadsheets option here. I don't fully understand how this works, to be perfectly honest, because it's just never been relevant in an exam or a SAC. I know some people have used them before to good effect, because you can use these, but it's just something that is so seldom taught that I've never actually needed to use it for things. So there is a way to do it. In fact, if we look at example 35, they probably tell you how to do it, which is going to be here. Yeah, they have a whole little guide on it. Put your things in that way, exponential regression, and it'll give you the coefficients that'll sort that out, the A value, the B value, and depending on the complexity of the exponential. In fact, you probably only ever need the A and the B, because as we said before, any coefficient K just gets shoved into here anyway. So yeah. Next up, nothing, actually, because this one is also a repeat. You got one unknown, two unknowns, 1 point, 2 points. Very similar stuff. Alright, and that's pretty much it for all the applications there. We're seeing some similarities. Some of the easier questions, you just have enough information to plug in and get the rule off rip. In a lot of other ones, you're solving for K to get the rule, and you're doing that by usually subbing in some sort of point, using whatever information is in there to sub in. Other kinds of questions involve giving you the rule itself, and then you just treat it like you've done any other function, exponential or otherwise, it doesn't matter. You still just handle it the same way. And this idea of limiting values, so that's going to be pretty unique to exponentials or anything that has an asymptote. Question: if we don't have anything planned for tomorrow, go through the SAC. Yeah, we can go through the SAC. That's fine. We can do that tomorrow. Easy. Cool. Yeah, let's do that. That'll be nice, because I've got my stuff as well, but obviously you want to do something that's very, very specific to your school. And it'll be good to see what other schools are doing as well, because there should be similarities across the board. I did have a look at that SAC, by the way. In fact, I'll pull it up for everyone just so we can get a preview of what that might look like. So, from my understanding of it, it looked fairly standard. They gave you a whole background on it, but in reality, probably the weirdest thing in this one is you have the subscript in the equation. That's also present in the equation itself, right? The definition of it is there as well. Um, that's all. It could have just as easily said C of t and then n was floating there. You don't really have to worry about the fact that there's a subscript there. It's more so just telling you more information succinctly rather than just saying n equals 0. They're literally having it there and showing you what happens as it condenses down. But you know, it's just, hey, what's server temperature? State period. Well, there it is. Range, range of function. Sketch, sure, it's just a circular function. Average value, that's your integral. How many hours is it over that? That'll be like a CAS solve if this is tech active. You just solve for the two spots where it's 20.25 and find the difference in time values. Yeah, so like these are things that aren't so bad. If you could explain the process for as many questions. Yeah, absolutely. We can go through this entire thing for the next lesson. We're doing SAC prep all the way down, basically. So unless anyone has any specific things, we'll go through this for sure. And even in the review class, if we run out of time to do the whole thing, because based on our... we've got a fair few of these done, but I suspect we'll need like a couple of lessons to go through the whole thing anyway. Because yours is due Friday afternoon, but it's the first part of the SAC, so the second part, you know, being able to do this stuff might still be helpful for you if we do it in the review. Let me know. Otherwise, yeah, that's time. So I'll keep that one in mind. We'll go for that tomorrow. And if anyone has any further questions, let me know. Happy to help. Yeah, Nihal?
Yeah, this is unrelated, but do we look at like finding the volumes of 3D shapes using calculus in methods?
Volume using... I mean, probably not in the way you're proposing, in the sense that you use your integrals over, what is it, double integrals or something like that. That's more like a uni thing, where you do surface areas and volumes via integrals. You can absolutely still do it with calculus in the sense of just by integrating functions, you go up from like rates of volume to volume and stuff like that. Uh, I don't think it's in the way that you're specifying that we do it in methods.
Okay.
Yeah, because there's all these equations, right, where you do like we set up your integrals in such a way where you can create shapes and find the volumes of such shapes based off of the integrals you set up. That's more of a uni thing.
Okay.
Hmm.
All right.
What brought that up?
Just thinking about. Like I've heard about it,
Hmm.
but I was just wondering.
Yeah. No, we did that first year uni in the engineering math class that we did. First year, first semester. You basically do like a kind of download in Spesh. In fact, Spesh might do it. I can't remember exactly, but you do very Spesh similar things in your first semester math uni class. Anyway, yeah. So
Okay.
most likely going to be showing up there or Spesh, one of those two.
All right. Okay. Yeah.
Sweet.
Have a good day.
Yeah, you too.
See you.
Thanks so much.
Thanks, Chris. See you tomorrow.
No worries. See you there. Hey Alex, did you have a question or did I bore you to AFK? Yeah.